for a good career, I think there's two possibilities for a good career. One of them, you can, of course, be the best. You're the best. You put in more hours. You work 16 hours a day. You don't have any hobbies. You don't have any friends. You just do the thing, but you're the best because you put in more time and you're also the brightest. In that case, do whatever you want. You'll be successful at that. It's just a little sad. And there's the other possibility, which is that you do something. You're maybe not the best, but you're the only one doing something. In which case, you don't ever need to compete with that person who like basically has nothing else in their life. You just like do your own thing and it's unique. And this quest for uniqueness, I think the way the world is evolving, it really rewards uniqueness.
Hello, everyone. Welcome to the Data Scientist Show. Today, we have Konrad Kording. He's a neuroscientist and a professor at the University of Pennsylvania. Konrad is trying to understand how the world and the brain works using data. He is known for his research in computational neuroscience. His current focus is on causality in data science applications. He also teaches bioengineers from all over the world how to make sense of data. Welcome, Konrad, to the show.
Thanks so much for having me.
So you started your research in physics. How did you get into neuroscience and later in AI?
Yeah, there was an interesting story. So I started studying physics. I really wanted to do plasma physics in the beginning, but very quickly it felt like biology was more interesting. And somehow I was missing something doing only physics. So very quickly, within just, I think, 3 terms or so, I started taking very serious biology courses at the same time. And that's how I, in a way, drifted away from physics into neuroscience. And then the physicists in Heidelberg, where I started studying, they didn't want me to do interdisciplinary work. They didn't want me to be a neuroscientist or anything else than a traditional physicist. So that's why I then moved to Zurich, because people there thought neuroscience was cool and part of physics.
And now as a professor in computational neuroscience, you're particularly interested in causality. And data scientists today can provide a solution by training complex models with large data set, sometimes even without knowing exactly how it worked. So can you tell us what is causality in machine learning and why you think it's so important?
Yeah, so when we do machine learning, no, we are making predictions, and we are making predictions that are often very, very good. I can, for example, take lots of people's clinical records, and then I can run some machine learning, natural language processing, deep learning, all the good things, and I can predict what's the probability that, say, they'll die next year, or what's the probability that they get some prom. And that is all good, but in reality, I don't want to know if I'll die next year. I mean, like, it would be interesting, don't get me wrong. We all want to know, like, how long we'll stay here. But what we really want to know, like in those cases, is what could I do so I'll be doing better? And that leads to this problem that's called confounding. So, for example, maybe people who like take vitamin D every day, on average, they live longer. What does that mean? Our machine learning algorithm will use taking vitamin D as a feature to that positively, because it's correlated with how long I live. And it will basically say, well, people that take vitamin D live longer. And implicitly, if you interpret the model naively, you can say, well, everyone should take vitamin D because people who have vitamin D, according to my classifier, they live longer. But in reality, there's this problem of confounding, which is, in this case, it could be that people of high socioeconomic status tend to take vitamin D, they tend to live long, and all of a sudden it looks like vitamin D makes you live long. And so that is the big difference. If I do prediction, I just want to be as good as possible, mean squared error, or whatever I use. Whereas in reality, I want to know what would happen if I would change something. What happens if I make you take vitamin D? Will you live longer? And that is the question that we want. So if I'm in business, I want to know, what can I change in what I do so that my products will be sold more often? I want to know which are the customers where if I would add an advertisement to them, they would buy my products. I don't want to know which of my customers both get advertisements and they buy the products, which is what we normally do with machine learning. So the real question that we want to do in business or science or engineering or medicine is always, what can I change so that the world is better for me? And that is a question that we can only get from causality and not from traditional machine learning.
So in addition to just predict what's going to happen, we want to actually change some policies or behaviors so we can, in reality, have better results.
That's right. Now, like, that's the nature of human existence. We're here, we're in this big, complicated world of lots of interacting things and podcasts and so forth.
Yeah.
What we are trying to do is find ways so we can change that world around us so that the future world is better for us.
That's a very interesting view of how we can use machine learning, not just use machine learning, but learn from machine learning algorithms to make the world better. So for people who want to learn about causality, do you have some favorite books or courses to recommend?
Yes, absolutely. So if you're new to causality, if you don't want to dive into something full of complicated equations, I can highly recommend Julia Paul's book, who is one of the pioneers of the causality field, but he wrote this delightful book. It's called The Book of Why. And it really makes causality and why we need to care be alive. And at the same time, it gives some intuitions on what's possible. And then otherwise, if you come from machine learning and you want to dive more into the technical parts of it, for example, Schulkopf's book is very nice, that highlights how we can bring machine learning techniques to causality and vice versa.
Yeah, thanks for sharing that. So for your research around causality and neuroscience, what are some interesting findings or projects you're working on?
Yeah, so there's one class of ideas. So causality, because it's so central to everything in a way, has many different subfields, and they have very different traditions and ways of thinking. There's an area that's popular in machine learning at the moment, Julia Paul and graphical models. A lot of people will have heard about it, but there's another field coming more from the economics tradition. And what they do is what's called quasi-experiments. And that's something that I find very exciting these days. So what's the easiest places where we can know how causality works? Well, it's things that we call A/B testing, where we do one thing and we do another thing and we see if the first thing was better than the other one. And that is because it's random, you can easily prove that it's causally correct. But there's lots of domains where we can't randomize things. Like we can't have a random set of people take dewormer and another people take vaccines or something when it comes to COVID and see what the outcomes will be. A lot of people will die. That would be very sad. And so we can't always run randomized controlled trials. We can't always run A/B tests. Now, the idea of quasi-experiments is that sometimes the universe does you the favor of actually kind of randomizing something for you. And let me give you an example for that.
Yeah.
So we call certain people high blood pressure. No, we say if your blood pressure is above 130, we call you hypertonic, and we give you drugs that lower your blood pressure. Now, we all know that there's some noise on that. So if I take your blood pressure 10 times, it will sometimes be 5 higher and sometimes it will be 5 lower. There's like some distribution of that. Now, what does that mean? If I take all people that are above 130 blood pressure, of course, the people above 130 will be doing much more poorly than the people below 130. But what I want to know is, does that extra drug that I give those people, does that really help? The problem is if I just compare those two groups, it's kind of nonsensical, because in the above 130 groups, we have like lots of very old and very sick people with very high body weight. Below it, we have the opposite. So, but the insight there, and it's a quasi-experimental technique, very popular in political science and econometrics, where we say, well, but what if we just take people that are 129 versus people that are 131? And it turns out that if we do that, if we make this be very narrow, then we can meaningfully compare them because there's some noise. That means that everyone who's at 129 could have been at 131. Mm-hmm. And everyone who's at 131 could have been at 129 because there's just noise on that. So that means that the comparison between those people that are just on those two sides is actually valid. And we can prove exactly under which circumstances that is the case. And it allows us to basically figure out at the margin, what is the causal effect of the treatment that we give to the people that we call high blood pressure versus those people that we don't. And this general strategy of looking for cases where the world gives you something random instead of you building in something random is very rich. And it's something that we can apply to brains as well.
Yeah, that's very powerful. I used to work on A/B testing for a few years, and even within A/B testing, sometimes you have a seasonality. You have other factors that it's really hard for you to completely control, especially in the real world. The data has so much noise. So with this quasi-experiment, I think it's very powerful.
Yeah, and the world gives us those. Now you can say, for example, let's say if I do search, you can say with every item that you could display to me, I associate a certain affinity score to me. And there's going to be some threshold that decides if I'm going to be first or second. This threshold allows us to do something like A/B testing without us having to automatically, without us having to actually randomize the order of things. And we can see what the effect is of being in the first page of search listings versus the second. So we can do a lot of these things without having to purposefully randomize things.
Yeah. And then it comes to me, people might ask, so with this quasi-experiment, how do you test whether your finding is the true causal relationship? Do you need to run a randomized experiment to test this again, or how do you know?
So quasi-experimental studies make some assumptions that you don't need to make if you do A/B testing. If these assumptions are correct, then then your findings will effectively be as good as if you A/B tested it. You will need more data because the statistical power is somewhat lower, but you can be sure that everything will be fine. Now, let's briefly talk about what can go wrong. Yeah. For example, imagine we're in this case. If you're above 130, we say you have high blood pressure. We need to treat you. But now, what if you're like at 131, and whenever you're a rich person, your doctor's like, I really think you it's good to treat you, and we keep it like that. But whenever you're a poor person, the doctor says, well, maybe let's redo the tests, and you redo it, and then half of the time you're at 129. Yeah. That introduces a bias. Basically, if people cheat in these things, then the results will be wrong. And so you need to make the assumption that there's not such cheating. Now, of course, if you're a search company, you know that no one cheats with your algorithm, or at least hopefully. And so there are cases where you can exclude that kind of cheating, but you need to test for that. In the same way, in fact, how you need to, if you do A/B testing, people usually think that it's easy. And it's not. So here's, for example, a lot of people now in medicine, we call A/B tests, we call them randomized clinical trials. Right. But there's interesting things that can happen, which is, what if some people just drop out? I recruit them, I say, you're treated and you're not treated. And some people just say, okay, I'm out of here. And in that case, if you're out of there, can depend on what you're doing. So if you run an A/B test, you might say, okay, and customers who like just leave before they can give us an answer, we don't count them. But what if the color of the font that you're currently testing actually makes them leave with a certain probability?
Yeah.
In the same way as like if I have side effects on a drug you're testing on me, I might just be like, look, I'm out of here. I've had enough of this. And so that means that if we do A/B testing, we need to make certain assumptions in the same way as if we do quasi-experiments, we need to make somewhat stronger assumptions.
Yeah.
And if we want to do what we call observational causality, we need to make even stronger assumptions.
Okay, yeah, that makes sense. Now you dived into machine learning and using causality. What are some research, machine learning research that trend that I think it's you wish more and more people could adopt? And what are some trends you think people should be careful, could be improved?
Well, one thing, of course, based on what we talked about before, I think people working on machine learning should start thinking about causality because it's important. But when it comes to otherwise, what are the useful directions in machine learning? A lot of it boils down to that we want to build systems with the right biases that we want machine learning algorithms that work well in the world in which we are. And of course, we all know the current trends. Now we take big foundational models trained by Google or Amazon or OpenAI, and then us as scientists fine tune those models. Those are the techniques that tend to work very well. And there might be a space, in fact, where we can combine those ideas with causality models.
So now let's talk about the brain. You're very interested in understand how the brain works. And when you started to use more neural nets, have you find that neural nets can help us better understand the actual neurons in the brain? Do we actually make decisions by minimizing certain cause functions in our mind?
Okay, this is a wonderful question. So there's one use of neural networks in neuroscience that everyone agrees with. Now we can use them as tools just in the same way as data scientists always use methods for tools, which is we analyze images with it, we analyze brain data with it, we recognize diseases, all those things is something that everyone agrees with. But myself and a couple of my colleagues go one step further, where we say we actually believe that what the brain does is in a way similar to gradient descent in a hierarchical deep recurrent system.
Oh.
And so in that sense, we do make that assumption. Now, it's very hard to be sure, not like if I take your PyTorch code or something, I can be like, okay, here's where Daliana defines the cost function, here's where the optimizer sits, and so forth. When it comes to brains, this is of course much more complicated. But let me maybe give you the gist of why I think that the brain probably does it. So the first one is when it comes to solving real-world problems. In the technical domain, we don't have many alternatives to something like gradient descent. Not like what do we use? All the algorithms that actually work seem to be going down gradient descent, gradients of something. So in that sense, you can say if I look at the models that are popular in neuroscience, they tend to not work in the real world. And in a way, I'm saying if a model wouldn't work in the real world, I don't think that the brain uses it because like the brain clearly works in the real world, at least most times. So that's the first one, that gradient descent like models do work. The second one is I think I can make an evolutionary argument where you can say, I could either encode how the brain learns, or alternatively, I can encode a mechanism that optimizes things and another mechanism which decides what we should optimize. Now, if I do that first thing, then everything is highly coupled with one another. So if I change the learning rules in some parts of the brain, I basically need to redo all the rest because they are all coupled with one another. Whereas you can say, if I divide those two, then the evolution can work much more efficiently. It can try a new cost function. It can say, what if that part of the brain optimizes this and that part optimizes that? And because the optimizer would be doing gradient descent, it could basically evolve independently of the rest. And this kind of modularity is one of the things that we see all over the place in biology, that you basically take problems, you modularize the solutions. You can say, we can take the immune system of one person, maybe some people have a great immune system, and the visual system of another person. And through evolution, ultimately, the good immune system will be combined with like the good vision system, and which will be combined with others. And so modularity makes evolution fast. And that's also something we, of course, know from machine learning. Like if we have problems that naturally fall into separating subproblems, then optimization is efficient. And in a way, evolution is an optimization algorithm itself. So in that sense, we should expect that level of optimization. And that's why the brain that's why we should expect that the brain does it like that. That's why we should expect that evolution evolved it. And then I have a third reason for that, which is for the last 20 years, I've been building models that basically ask, how could the brain, with all the properties that we know about it, do something like gradient descent? And there's realistic proposals now by multiple people, including Blake Richards and Richard Nord and Jeff Hinton, of course. And so a lot of wonderful people worked on how the brain might be doing it.
Yeah. Oh, that's so great, because I'm so excited to have this conversation with you. I have this puzzle in my mind. Just for example, say for example, the first time I give a public speech, and then if some people made fun of me, that become a traumatic experience, and I'm going forward scared of public speaking. Even though, say, in the future, I gave some speeches and those went well, I still have that data point that in my brain, I give a unfair amount of weights. However, in my brain, I cannot just say, hey, can you just be a LSTM algorithm and then put it in a forget gate and forget that data point, because it doesn't serve any purpose for me, right? And then I'm not a neuroscientist, but based on what I understand, I think because our brain, part of it is try to protect us, optimize on safety. So it holds on to those data points that reminds us, oh, if you speak in public, that might be dangerous. And then my question is, those type of protection around physical safety is from our old, cavewoman brain, but it doesn't serve a lot of purpose in our modern society anymore. I want to optimize to take some calculated risk, to be more successful, to forget those past events that doesn't help me anymore. And I can't wait for more generations to optimize based on this modern society. So do you think in our lifetime, there's some way our brain can be connected to some computer, and then we can pick and choose what type of optimization function will serve our purpose to make us happier, more fulfilled?
This is a wonderful question. At the moment, let's give a little calibration here. At the moment, our understanding of the brain is very limited. Why is it very limited? We get data out of brains, but no one gives us an interpretation of the data. Yeah. So far, there's a small number of people who even believe that the brain does some cost function optimization. But you're absolutely right. If the brain does cost function optimization in a way, then we should expect, in a way, these loss functions that are implemented in our brains to be something that we can do something about, that we can potentially change. Now, I'm not sure if you would want to do that. No? So at some level, what does it mean that you're you? In a way, it means that you follow your own objective function, that you have your own loss function. Like right. We all have somewhere in us this function that tells us what we mean with the world being good versus the world being not so good. What you're asking for is that someone goes and changes what your cost function are. Now you can say you don't like that the cost function that biology endowed you with is effectively risk averse. Not like you can say you don't want to like repeat this like bad experience of giving your first big talk in front of lots of people. Mm-hmm. And I think we all have that like these bad things that happen, they're like over salient. Yeah. But that's protecting us from stuff. It's protecting us from being eaten by this lion that is sitting somewhere. Yeah. Like there's a good reason for that. Now you can say the world in which we live now is like different, as you said. Right. I love that analogy from that cave person's world. But we don't know how it's different exactly. Like there are still dangerous things in this world. They're just dangerous in a different way. So I think a lot of the things that make us these amazingly successful creatures is this complexity of the loss function. In fact, if we look at the history of machine learning, not like what's happening, we become more sophisticated in our loss function, not like maximize the probability that we recognize a face. Oh my, like we just produced like a super racist like machine learning system. Yeah. There's all these things that are going wrong, and in parts the reason why they are going wrong is they have these simplistic cost functions, maximize the R squared or something, where in reality we are born into this world with this super rich cost function. Not like we are like curious and we like other human beings and we like some level of dependency on our family, but not too much. And in this like level of complexity, if you allow people to edit that, they will be making a lot of mistakes at first. So I think if you could change the cost functions in my brain, I wouldn't want you to.
Okay, that's a great answer. But now I'm curious, if you could, is there any part of the loss function you would change? You want to optimize more for your life?
In my own life, I don't know. Not look, I'm a very imperfect person. Like that's the nature of human existence. But if I messed with it, I wouldn't be my authentic self anymore. So I don't think I would want to change anything there. Yeah. Like giving me like some superpowers would be good. Not like give me perfect ability for empathy or something. That would be awesome. Or like, although that might be, but like now that I think about it, if I had that life might just be hard. Like you walk around, you understand the misery everyone is in. Maybe it's like good that I don't have that. So yeah, no, I don't think I would change anything.
Yeah, I actually agree with that.
What about you? Would you change anything?
That's well, one thing I definitely want to change, if there's some cost function can allow me to find the same sensation and joy from eating broccoli, just like I'm eating French fries, that would be great. So I can eat more healthy without worrying about anything. But now, previous, I was thinking, I can optimize being more productive. I like that you mentioned having more empathy. And also maybe I want to forget about some past experience that doesn't serve my purpose anymore. But now I'm influenced by your answer. I think now I'm like the Bayesian algorithm, taking your prior, it changed my decision. I think I don't want to change that part anymore. Maybe just some minor thing. Maybe I can also, a minor thing like the type of food I eat, but not on the personality level. Maybe I can also change my hair color so I can be like you. Sometimes my hair is blue, sometimes it's purple.
But let's talk about the fries. If you really wanted that, I have a solution for you. We put like some poison into fries that makes you vomit big time after eating the fries. You eat the fries, you will, there's a very strong built-in bias of people, like any food that you kind of vomit on, like you will not like it much more in your life. Yeah. So if you really cared about like getting rid of like your love for French fries, you could, but in reality, they're like crunchy and just scrumptious and they're just not like fries. There's something really good about fries.
Yeah.
I wouldn't want to give up on like that feeling and that satisfactory feeling of like of fries in my tummy. There's something good about it.
Yeah. Yeah, right. Maybe not giving it up, but just find more joy eating healthy vegetables. I love that. Someone on Twitter provided a lot of great questions for me, and one touched upon evolution you mentioned. So if evolution is just gradient descent, or if it needs the brain to become gradient descent, what do you think about this? I think you talk about it a little bit.
Yeah, let's talk a bit about evolution and gradient descent. Like we talked about like why evolution is plausible, makes gradient descent more plausible, but let's talk about evolution itself. So I argue somewhat controversially that evolution in a way is gradient descent. And let me highlight what I mean with that.
Yeah.
At any point of time, a species consists of lots of different locations, if you want, in some phenotype space. There will be some taller people and some shorter people, and like some in people with like different hair colors, and people with okay, that's not evolutionary specified, but people with all kinds of different properties.
Yeah.
And now you can say in this world there's certain dimensions where things could be helpful for fitness. Now you can say maybe there's a new domain where conserving your energy is really useful. So you have an environment that makes that basically adds loss to being big. And you could think of other environments, maybe one full of like very aggressive people where like being really big is like really good. And you can say, what would happen in those cases? No, you would have effectively that people in the first case, people that are shorter, will be more likely to live and have offspring. In the other case, like bigger people would have more offspring on average. So what we would expect for the overall population is that in one case it drifts towards shorter people, in the other case it drifts towards longer people. You can say that if we have multiple axes, now it's not just if you're short or tall, but it's on if you tend to be extroverted or introverted, or if you're like funny or not funny. You have all these different dimensions. And if in that space, in the rough vicinity of where like that cloud of people lives in a way, if there is a direction in which things get better, then on average, the population will drift in that direction. And under certain circumstances, this drift of the overall population will approximate gradient descent. That's what I mean when I say that I believe that population dynamics, that evolution in a way can be well modeled by gradient descent. And it allows me to make predictions. Now I can say, if I look at the world and wow, the world in which we are is that like short, funny people do extremely well in this environment. I expect people to become shorter and funnier over time. Yeah. So in those domains, that notion of gradient descent can bias a certain amount of aspects of the world that we can describe.
Yeah. And why did you say that is controversial? To me, it makes sense.
So I think what's controversial is just the framing of it. Now you can say, if I look at an individual person, are you, Daliana, going down the gradient of something? Like, no, you're just leading your life.
Yeah.
And so I think what makes it controversial is that for me, evolution is a learning problem. And that is because I think about one population in a way.
Yeah.
And that one population changes, and it changes in potentially predictable ways. And I think a lot of people, they think more like about individual beings. And of course, an individual being doesn't do it. And I think that there's just like a certain amount of misunderstanding there.
Yeah, I get what you meant there. It's like a statistical findings. When you draw conclusion on the group, you cannot use that to infer just a individual. It only makes sense when you talk about the group, the certain population. So it's not specific for me. I might just trapped in a local minimum maximum.
Well, but like, no, that's the interesting thing, that there's these two time scales. You can say, we change ourselves in our lives. It's almost like we run some, not at least the way I think about it, we run some kind of an optimization algorithm on ourselves. And that makes us better in the niche that we are. What do I know? Like, I'm a professor. I found that drinking a lot of coffee makes my life better. Over time, I drifted towards drinking more and more coffee, and now life is pretty good. And so there is this optimization, if you want, locally that each of us do. And then there's kind of that meta optimization where like evolution acts over the population, and arguably both of them, we might see certain notions of gradient descent there.
Yeah. And the coffee drinking might be a confounding factor.
Indeed, yeah.
And then, so someone also mentioned, why are the "it won't be much work" activities and initiatives totally engrossing and worth every nanosecond of effort and make you believe in humanity? I don't have context of this. Do you say it won't be much work a lot?
Okay, this was one of these comments that we'll need to talk about a few minutes before we can even get there. So let's maybe first briefly talk about NeoMatch Academy. So NeoMatch Academy is this wonderful summer school. It lasts 3 weeks. In fact, there were two of them in this year, a summer school in deep learning and a summer school in computational neuroscience. The way it works is students are in groups. And in fact, for a lot of listeners to us here, like this is a wonderful training opportunity. So you always learn in a group with 10 students and a TA, that teaching assistant we pay as an organization. And in that group, the students really help one another grow and become good at learning, in this case, deep learning, or maybe computational neuroscience. And then we have a large number of volunteers, literally hundreds and dozens of professors, who basically say, what if we don't do our teaching materials the way we usually do it, where we teach it to like maybe 30 people, but what if we are really obsessing about making the teaching materials awesome and fun and well calibrated and meaningful and deep and not wasting students' time and all that. And so that team developed like these wonderful teaching materials. So that's what NeoMatch Academy is. Now, the comment relates to a rumor that is not true, which is that so a lot of the early people in NeoMatch Academy were people that I kind of pulled into that group. As you might know, I'm like a people person. I like talking with people. I know a lot of people. I love talking with people. I get energy from kind of sitting with people and talking about things. So I brought in a good number of people into the organization. And now a lot of these people we brought in for doing something simple, like, can you help us like set up this thing or teach this little thing? And a lot of people ended up becoming like really big volunteers that ended up doing really, really difficult things. And so out of this came like this joke that everyone always said that, oh, Konrad said it won't be much work. I never said to anyone it won't be much work, as far as I know. But like, it's kind of a running joke where they make fun of me. In fact, they printed it on all the T-shirts, not like add insult to injury. So all the NeoMatch Academy T-shirts on the backside say, it will not be much work. But of course, and that brings us to that third part. Why does it make us believe in humanity? So what we have there is that hundreds of people kind of jointly decided, let's work together, make like the most inclusive summer school that we could think of, which meant like we ran in 12 time zones, 110 countries this year. We have materials translated in different languages. We have learning in 10 different languages also. So it's like this incredible, like multifaceted, big group driven thing. And that's why Megan, I believe, said, why does it make you believe in humanity? Well, there's lots of people kind of, they all have day jobs. They're all professors or students or postdocs. They work for Google or Facebook or like one after the other, or just sold their startup or just working on their startup. all these domains, so they're just data scientists somewhere in industry. All these guys kind of came together and said like, okay, let us teach this thing as good as we can. Yeah. And that is really heartwarming. And I'm really in awe of that community that really help one another learn. And that's why it makes you believe in humanity. Yeah, that's wonderful. So you teach this data science course to bioengineers, neuroscience students. How's that different from a general data science course? Okay, so NeoMatch Computational Neuroscience, the school, that is, if you want, it's in significant parts data science for neuroscientists. And let me tell you something about my philosophy of human learning. In a way, we learn best if we learn about things that are meaningful to you. Not like if you're a neuroscientist and I give you like a generic data science course, which just says, okay, here's how to run a linear regression, and here's the power, or like here's regularized logistic regression. I'll be like, okay, fine, yes, okay. But if I'm like, hey, you're a neuroscientist, you want to know how you can predict what a neuron will do next millisecond. How could you do that? You could use logistic regression to do that. What would be the right inputs? Like, it comes to life for you. Yeah. And I think that whenever we teach data science, we need to bring it to the students based on the questions that they are interested in. So if you are interested in finance, you should be thinking about portfolio organization as a motivation to learn about principal component analysis. And if you're if you're like a bioengineer, you might be motivated thinking about organoids or something like that. And I think we need to really bring people we need to start with the prompts. And I think this is a big problem in data science teaching, that we tend to teach the methods instead of picking people up with the questions that they have. Now, how was your experience when you were first learning data science? Yeah, when I first learned data science, I felt I was learning a completely different language, probability theory, and the example in our textbook were unfortunately very unrelated to my life. So I felt very unmotivated. For example, for Bayesian algorithms, we're learning based on some factors, can you predict the pattern of the cows? I think the author of the book have a lot of research in farms. Those are cool. I love cows, but I just don't know how am I going to use it when I actually have a job. So my GPA in my grad school kind of just went down spiral, because in the beginning I was motivated, I was scared to fail in classes, but later on I just don't know how I'm going to use it in real life. I just couldn't wait to get over it and start working in the industry. And then when I started in the industry, I actually realized those very dry theories and algorithms are very important. So I have to go back to and learn. And then that's when I feel more motivated. Nobody asked me to submit homework, but I learn it because I know it's useful. So what's the best example of a Bayesian question that you encountered as a data scientist? Yeah, so the Bayesian algorithm was, I think, when we design A/B testing, sometimes for example, the results is not significant. The p-value is greater than 0.05, but businesses still want to make decisions based on the experiment. So we're like, okay, if the statistical testing is not helping you, maybe we can use some Bayesian algorithm. If the benefit you draw is greater than, looks better than the average of the same type of product groups, and then using how the average performs as a prior, and then we derive the posterior to see what is it like, and then we give the Bayesian confidence interval to help them make decisions. So that's how we use it in real world. So learning it would have been much easier if they had started with that, not like where you could say, there's a company, they are running user tests.
Yeah.
They run 2 user tests, one on group A, one on group B. How do we combine those 2 tests?
Right.
Because they now want to know what's really going on. And I think that that is an important problem in teaching. And that's why, say, the computational neuroscience schools basically teaches a lot of data thinking, but with neuroscience examples to a neuroscience audience.
Yeah. And for people who want to learn data science but don't know where can they start, specifically, how do they find those type of engaging courses? What's your advice to them?
Well, I'm starting to build a curriculum. It will all be like all the materials that I develop. It will all be in a Creative Commons open license. All my materials will always be out there. But I think the best thing you can do at the moment is there's now a lot of people who teach data science topics. And with a little luck, there's someone who's interested in similar topics to you, who is working on, who is using the right questions kind of to motivate how everything goes. But I think there's also a cultural problem. Like most of the time, data science courses are taught by computer scientists, and I love computer scientists, and I teach deep learning at UPenn in computer science.
Yeah.
But computer science scientists tend to start with the abstract concepts, where I think a lot of students learn better by starting with concrete questions and then generalizing from those questions. And so that, I think, that has an influence on the quality of the materials. One course that I like very much that is, I believe, also mostly open or maybe completely open is the San Diego, UC San Diego has a wonderful course. It's meant for cognitive scientists, but it therefore uses a lot of these examples that are like meaningful to us, not like how do people think, and like those things. And that is one that is designed very well for a broad audience. But yeah, it's a real problem, no? That there's no mindful curriculum development in that space generally.
Yeah. It's very interesting. It seems like people who work in neuroscience have better knowledge on learning theories, so they design more mindful and engaging data science courses.
I don't think that that's because it was neuroscience. I think what happened at NeoMatch Academy is just that normally you have one professor designing a course, or even say a YouTuber who designs what they do. They will still be alone in a way, not like there's the big course and it's them, and they don't have much time for that. So what we did very mindfully at NeoMatch Academy is for every day, what we basically try to recruit the world's best professor in that area and counseled them to help them kind of build a course that people could understand. And thereby we divided the load over a lot of shoulders. And if you divide the load over a lot of shoulders, it gets much more doable than if you basically have that one person who has to do everything. Yeah.
And you love teaching people how to make sense of data. Do you think everybody should learn data science?
Yes, I think that, look, we live in a world that is more and more defined by data. Not like what if you use a search engine, it uses data to decide what to show you. If you go on Twitter, it's a search, it's an algorithm that shows you what you see. If you go to LinkedIn, there's an algorithm that decides that all your listeners will be seeing your things as opposed to someone else's.
Yeah.
In a way, we are surrounded by data everywhere, and the world around us is reacting based on data. And if we don't understand data, we could just as well be blind in this world. So in that sense, I think in a world that is more and more determined by data, we need to understand what's behind it. And what's behind it isn't very complicated. Like, people are dazzled by the math that people put up there, but like, that is not the important thing. The important thing is they basically try and estimate something. The difficulty isn't what algorithm do they use to estimate if you're going to click on this banner. The thing is that you need to know the banner is displayed because there's an algorithm behind it that says the probability that you're going to click on this banner versus that banner is higher. And that's why it shows up there. And so in that sense, I think that data literacy is something that every human being should have. Certainly everyone who goes to university education. Look, why do you go to university? You go there because you hope that it explains life to you in a way that it clarifies the world that we live in, and that it helps you be more productive in the world. Now, clarifying the world, you need to understand data to understand what's happening here. And you also need to understand data if you want to be successful in most careers. Like a certain amount of data understanding, I presume you don't have many colleagues that haven't been trained in data, no?
Yeah.
And so in that sense, yes, we should demand of the, we should make it fun, easy, and useful for people everywhere to learn about data science.
Yeah, I agree with you. I hope more people can learn about data science earlier in their life. Maybe in school doesn't have to teach them, how to derive all the theories, but on a high level, maybe use some analogies, storytellings, and then teach them how to make better decisions using data, or at least, like you mentioned, aware of those applications that are using their data that will affect their daily life. I think that would be very helpful.
Yeah. And it comes with this whole ethical problem as well. Like, these algorithms are being used. These algorithms are optimizing some loss functions.
Yeah.
It's not that you or me decide what the loss functions are. They often implicitly the numbers of dollars that are there. Do we want our society to be organized like that? And unless the general public gets educated about how data is used, they cannot have an opinion about that. But say, if we look at radicalization in the space at the moment, it is driven by algorithms that basically keep introducing you to people that are just like you. And in the end, it breaks the connections in society. And if people would really understand how data works, they wouldn't be fine with that. It's just that if the public doesn't understand it and the companies optimize it, there's no one who can keep them accountable for it.
Yeah. And for your students or some other data scientists who are currently not in biology or neuroscience, what are some very exciting fields in neuro research or applications that you think data scientists might be interested in getting in?
Well, I think the first thing that data scientists need to know is the speed with which availability of data is getting better. So it turns out that the number of nerve cells that we can record from has been growing exponentially for a long time. And all of a sudden, there was just a paper that came out, I think a few weeks ago, from Ali Pashivaziri's group, who showed that you can record from 1 million neurons at the same time. So they have these little dots in every cell, and then they can use optical methods to basically see how active all those cells are. So all of a sudden, if you want, brain science is moving into this big data age. So that makes it much more interesting from a data science perspective. You can start saying, okay, what can we understand about that? And all of a sudden, there's a lot of commercial companies in that space as well. A lot of people will have heard, of course, about Neuralink because of Elon Musk founding it. But there's a lot of other great companies in that space, including Kernel and Paradromics and many other companies. And I think this activity, Facebook is active in that area all of a sudden. And And so there is renewed industry interest in that space. So in that sense, what I want to tell data scientists is doing neural data science actually may have a future, which is important, of course. And the other thing, however, and I like to give the good and the bad, is data scientists often believe that neuroscientists really understand much about how the brain works. And let's say we're still pretty far away from it. And that is good and bad. It's good in the sense that we aren't going to lose our jobs anytime soon. There's still going to be data about brains to be analyzed 100 years from now. But also it's bad. It's not that we're at that level, Deliana. You mentioned that earlier. Can we like change the loss function that's in your brain? No, we're not there yet, which is sad because we can't deliver these things yet. But that it's fun because that means that there's something truly exciting to be discovered.
Yeah. Thanks for sharing your insights. And okay, now let's fast forward to a few hundred years later. We finally figure out the brain. Yeah. And you mentioned we don't really want to change the loss function or optimization in our brain. So when we actually say figure out the brain, how are we going to use those information?
Lots of different things. Now, like you can say, if we really understand meaningfully how the brain works, one thing that we can obviously do, we can build brain-like entities. That, of course, immediately leads us into a major ethical problem, because if we could build a human-like brain, like it would technically be slavery, like we basically build these things, we would probably demand that we can control what they're allowed to or not allowed to do. And which reminds me of one of my favorite films, Blade Runner. Like it's exactly that idea. Like, what does it mean if we can build these things that like kind of have human-like intellectual abilities? What would be our interaction with them? Like we build them, so they're robots. We usually think of robots as expendable. It's kind of these things. We build it, we understand it. Like therefore, we have the right to do whatever we want with it. So that building is problematic. But like it will be possible. Maybe we can build simpler things where that's less of a problem. But the second one is, of course, we can then deal with things that we understand as problems. Now, as I told you, like I wouldn't see a reason to like overly mess with my brain, and neither that of most other people, because like as long as people are like highly functioning, they're reasonably happy in the world, like basically messing with them, it's a loss of authenticity. And I think people kind of like underappreciate this level to which like this weird space in which we find ourselves that's like deeply suboptimal, maybe that makes us, and that kind of makes us into the interesting people that we are. But you can say that there's certainly subsets of people for which there's maybe problems that are big enough that they basically say, look, like this is not working for me. And you might be able to help them in that case. And we're starting to do that. And like if we give people antidepressant drugs, that's already that. And like it's kind of like we're trying to like hack them into a more positive mode of existence. And of course, as we make progress, we will progressively get better at those things. Now, like it's of course very blunt. Like, why are we sad about the world? It's kind of there's things in the world that aren't like they should be. So there's like lots of ways, lots of good reasons to have thoughts like that. And the question is, what's the nature? Like, do we want to? If people are sad in the world, do we want them to just believe like, oh yeah, it's all good? Arguably, that's not what we want. So so we need to think very deeply what we want there. But there's clearly cases, like if people have depression that's too extreme, or maybe people have other brain diseases, they have epilepsy. No one will doubt that if we understand brains well enough and we can make epilepsy go away, that we should be doing that. Like, of course we should be doing that. We're trying to do that. My colleagues here, like Brian Litt, is building like wonderful devices to like is working with wonderful devices to help patients with epilepsy. And I think progressively we will get stronger at doing something about diseases like that. Or for example, let's say people have a stroke. There's some people that have a stroke that basically they would like to be able to talk, but they can't.
Yeah.
If as brain technology improves, we can look into their brain, get the activity out, figure out what they want to say, give them like a prosthetic speech with which they can talk with the world. And we are doing these things. We're making progress in those areas. Or let's say they had an arm amputated. We've all seen Star Wars, probably. Have you seen in Star Wars the prosthetic device of Luke Skywalker?
Yeah.
And like in that case, it looks just like his regular arm. There's just one scene where he like screws open his arm and shows us that it's actually a prosthetic device. And I think we will be progressively over these. You said you promise hundreds of years, so I'm with you then. If we get hundreds of years, in hundreds of years, we will have a Luke Skywalker type prosthetic device that's as good as the real thing. And so we'll progressively move to that, and on that path, there will be a lot of science opportunities to understand better, and a lot of engineering opportunities, and a lot of commercial opportunities. So it's a bright future.
Yeah, it's very exciting to think about those possibilities. I really wish I can just fast forward to a few hundred years later.
But you'd be missing all the fun on the way there.
Yeah, that's true. The journey is also interesting. What we're figuring out is also interesting. So that's the future of brain. And what do you think of the future of maybe like a near future, maybe 10, 20 years of for neuro AI?
So what do you mean with neuro AI?
Oh, this is someone posted on Twitter. So I thought maybe someone follow your lab. I think maybe computational neuroscience. Yeah.
So not like and with neuro AI, the reason why I asked is there's two directions. You can say we can look at the brain for inspiration to build better computational systems, and we can use computational techniques to better understand what's going on in brains. And I mean, when it comes to the future of it, as I told you, neuroscience, the experimental techniques are advancing very quickly. We get more and more data. What does that mean? If we get more and more data, we need to now basically start using data science methods to analyze neural data. Now, if you have 3 neurons, you can just plot them and you can see how they look like. If you have 3,000 neurons, you can't. You need to ask, okay, should I do principal component analysis? If I should do principal component analysis, what does that even mean? Like, what does it mean about brains to have these things? What is the right language in which we want to understand the brain? So there is, in computational neuroscience, we use more and more of these data science techniques as part of the business of asking how the brain works. And that includes things, say, I can take one neuron and I get lots of data from the neuron. And then I can say, well, can I predict what that neuron will do based on maybe how Konrad moves, or maybe based on the activity of other neurons? So there's these things, we call them encoding models. And then you can go the other direction. You can say, well, let's get the 3,000 neurons that we have, and can I tell you what Konrad currently is trying to say, or what Konrad actually currently is saying based on what these 3,000 neurons do? We call that decoding models. And so all that space is developing very rapidly. But the other spaces also get developing now, where people say, okay, deep learning is maybe currently the state of the art for a lot of data science applications. What are the things that we can learn about brains that can kind of inspire us to build more interesting, more meaningful deep learning algorithms or non-deep learning algorithms? I always have that debate with my friend Josh Wilgelstein, where he's like, why do you always want to do deep learning? And we can learn from brains about deep learning and non-deep learning, like algorithms. It's an interesting space.
And a lot of people are interested in how did you get to where you at today? What do you have? What advice do you have for young researchers?
Yeah, okay. There's a whole bunch of advices. Let's maybe start with like the highest level. So I'm really curious about the world around us. And I think curiosity gets you a really long way. So I have, say, applicants to the lab or something that say, hey, I'm a data scientist. I really want to do neuroscience. And I ask them, so which books about neuroscience did you read? And they'll tell me, oh, I didn't ever read any books about neuroscience. And then I'm like, okay, but which papers did you read? I mean, like, if you say you're interested in neuroscience, you must be interested in neuroscience. And they're like, yeah, I don't know. I read like one paper at some point of time. Curiosity brings you a really long way. Like, whatever it is that you're interested in, like if you're interested in finance, read books on finance. If you're interested in bioengineering, read books on bioengineering. If you're interested in neuroscience, read books on neuroscience. And if you're interested in causality, which I happen to be, read books on causality. There's so much knowledge out there and there's so much material. So this kind of, we need to be thirsty for information. We need to have like things that are we need to make it our passion. If it's just something that we do for a job, it's very difficult to get excited about it. You know, like at some level, once you like think about like, okay, users, what can I learn about the users? It's kind of like, for you to get excited about something, you need to like develop a passion for that thing. So, and that's what like led to this weird trajectory of mine. Like I started as a physicist, got into biology. The biologist wouldn't let me. I got into like real neuroscience. I was into neuroscience. I was like into, okay, do I need Bayesian statistics to that? I was to Bayesian statistics. I went into psychology. I kind of moved between all those areas. And it was always just like, I see this thing, I'm like, wow, this is like so cool. Let me learn about that. But then let me also not give up on who I am. So in a way, in all those areas where I bring, I'm kind of asking these naive questions. I'm kind of like, okay, but like coming from there, how can I be sure that you're not overfitting your neuroscience data? Like, and then they're like, overfitting, what does that word mean? And so between those fields is often where the interesting things happen. So I think there's the next thing that I want to say is, for a good career, I think there's two possibilities for a good career. One of them, you can of course be the best. You're the best, you put in more hours, you work 16 hours a day, you don't have any hobbies, you don't have any friends, you just do the thing, but you're the best because you put in more time and you're also the brightest. In that case, do whatever you want, you'll be successful at that. It's just a little sad. And there's the other possibility, which is that you do something, you're maybe not the best, but you're the only one doing something. In which case you don't ever need to compete with that person who like basically has nothing else in their life. You just like do your own thing and it's unique. And this quest for uniqueness, I think the way the world is evolving, it really rewards uniqueness because like there's the weirdest jobs, you know, like the generic data scientist. Who wants to hire generic data scientist? Maybe you like know more algorithms than the next person, but like that's not like useful. That's not what companies want to hire these days. They want to hire someone who is like really passionate about this crazy application of data science to the way people move their hand or something. There's like lots of these jobs that take like something very specialized. And so I think if you want to be in data science, you need to combine, more and more, combine this data science with kind of this specialization, with this curiosity about something that's outside of that. And so that like not wanting to be generic, I think that that's very important. And people always have these wrong generic assumptions. Like they're like, I want to learn deep learning because deep learning is better than linear regression. And I'm just like, no, it's not. You don't understand what deep learning is about. Now, like this idea that like we can just be better, that's impossible. Like the salt is, if you want, at the place where these different ideas meet. And for that you need to be curious and you need to like dare to be different, you know, like dare to kind of combine something that no one else does with data science. And I think that that's missing so much, that not like how many data scientists, like they like take a first data science course, then they do deep learning, and then they do GANs now, like so many neuroscientists, always that same thing, but like they only know GANs apply to like vision. They don't, the fact that maybe there's like so much open space in looking at music and dance. No, that's like that's not the path. They all go the same path. They need to, they need, I think people need to follow their heart. And like suddenly I followed my heart, and that led me to this like totally weird set of places.
Yeah.
And I think I want to encourage everyone to like follow the heart in a way, but also like, of course, no, like that was always a big part of how I got there. But the other one is also like, it's a journey that we do together. So I was one of the first trainees of a bunch of professors in a sequence. And that was great because these guys had small labs. They had time to look, to think about the things with me.
Yeah.
They all did wonderful later in life, but like I was like among the first. I was one of the people that they were willing to invest in. And there's this huge bias that students everywhere have. They want to work with these famous people, but these famous people don't have time for them. They become generic for that.
Yeah.
Where they could choose like this small lab doing like this like slightly weird thing where like they have like a hungry young professor,
yeah,
and they learn so much more.
Yeah.
So those are just like a few vignettes in a way of like how I got here. But for me, it's very much about community and curiosity, and about wanting and accepting to be different. And of course, people shouldn't take my words for any of that, but I want to, there's a super famous computer scientist called Dijkstra. And in fact, if anyone listening to this doesn't know about Dijkstra, you should look up Dijkstra. Dijkstra has 3 rules about doing good science. And I try to live by them. And the first one is very simple. If you want, we always want to do the hardest science, the hardest research that we can live with. If we do something that's too easy for us, then we don't advance as thinkers. And so that's the first one. And then the second one is, if you can do something that's important for society, or do something that is good. Do the thing that's good because at least something gets solved well.
Yeah.
And I think that that's a very important criterion, that people often want you to do things. A lot of things get done badly, in particular in data science, where data scientists don't solve the real business problems, where they just cobble something together that doesn't in the end provide value. And I think we need to demand that what we do is really good. And I think that therefore this Dijkstra second rule is really important. And then here comes the last one. If there's something that you could do that given a little bit of time someone else will do, don't do it. Do something else. And I very strongly believe that. And I believe that to be the case for a scientist, where you can say, no, if someone else does it, like let them do it. I do my own thing that is unique. And if whatever I do becomes popular, I move to the next thing. Because it wastes time. But it's the same thing with companies. Now, let's say you do a startup company, another startup company does something that's very, very similar to you. Well, there's another possibility. You find a pivot to something else that is much more promising. And so when you find out that like you're in a space where many people want to do the same thing, it might be a good opportunity to just move somewhere else. Yeah. So I try to live by all 3 of Dijkstra's rules.
Yeah, I think it takes a lot of thinking and reflection for us to figure out what makes us unique. But sometimes we're in the chase of the next level, whether it's a promotion or, you know, it kind of sometimes we get lost in there.
So you're doing something very unique, combining communication, career advice, and data science. How did you choose that niche?
Oh, you're turning the mic to me. Sure, I can share a little bit. I have been a data scientist for 7 years, but I think since when I was a kid, I always enjoy having conversation with people, and I like different type of performance arts. I don't think I ever shared in public before, but in college, I used to be in a drama club.
Oh,
so
wonderful.
I used to act, direct drama. And then when you have the title of data scientist, you kind of just forget those past experiences, especially in my early career. I do feel I need to work hard to, catch up, to make sure I do a great job. Because when you're young, you just have a lot of insecurities in your life. And now I think I'm in a place where I feel, oh, I don't need to constantly prove myself anymore. And I feel I'm more than just my job title. Who am I really are? And through the exploration on my blogs, posting on LinkedIn, social media, I realized, oh, I really enjoy building a community and impacting a lot of people. And sometimes I have conversations with my other data science friends. I just realized, oh, if I record this, there might be a lot of other people that can benefit from it. And it also give me an opportunity to have a conversation with interesting people. If I don't have this podcast, I will never meet you, for example.
Yeah. Look, we're living by very similar ideas then in the end. Like you took what's like unique in your background in a way.
Right.
And you made it be really valuable. And it's not that data science itself is the valuable thing. It's like that data science together with like this directing and acting and kind of being with people that made this be so awesome.
Yeah, thanks. Yeah, that's what I'm thinking. So I want to experience that, combine my deep knowledge in data science and my people skills and my interest in community. I think this is a great path for me to explore and iterate.
Right. It's so interesting. No, like we are in such different places, but we both in a way live by the like, have your be your unique you, but also in a way there's like there's you do it extremely professionally as well. Like there's like you suddenly live by Dijkstra's rule to do it well.
Thank you. I do think it's very important for us to not be defined by our job title, right? Not be defined by the major we studied in school, by how other people label us, give us the some opportunity, maybe some space in our life to learn new things and then figure out who we really are. And
I want to emphasize for everyone, like data scientists, there's this idea that if you're a data scientist, you must have studied computer science and be like very narrow in that area. This is exactly not what the world actually wants. Like they want people who can like carry data science skills, but bring it to other places. And in a way, like in my role as professors, I bring data science to like all these corners where they don't have data science, which is awesome because I can be totally mediocre and I will still be the first person doing something with data science in the area. And therefore, like, it's really awesome. And I think that like this, that it's so important to emphasize that it's how successful you're as a data scientist. It's not a competition who's like best at the very specific computer sciencey data science things. The reality of using data for science and being a data scientist is that everything happens between the domains. And like, of course you need those strong data skills, but you also need the domain expertise and the ability to intermesh with the team and so forth. And I think people forget that. And I think that it's scaring a lot of people away from a career in data science.
Yeah, that's a really great point, because also, like you mentioned, a lot of people taking data science course and then they think the next level is to learn deep learning and then GANs and some other more advanced stuff. And we sometimes forget we learn that as a tool to solve interesting problems. And then when there's a problem, if we can solve that using simple method, we don't have to use deep learning. Of course, it's always great to have the tools in your toolbox whenever you need to use it, but I think we need to think about how can we be problem focused or data focused instead of just like, oh, I want to use this cool tool, which I'm not innocent of. When I just learned those, I want to, it's like you have this hammer, you just want to solve any problem with that. And also the point you mentioned, how do we use data science in a certain domain, because with the development of different type of data science tools, it will be easier and easier for people to apply data science. And what differentiates great data scientists is the domain knowledge, how much they know in a certain area, so they can be creative and find solutions for that specific domain. So my advice for data science, it doesn't matter what industry or company you're working at, don't just hang out with data scientists, hang out with the engineers, with the product managers, sales, see how they work and make friends with them. That will make you a great data science or a great entrepreneur in the future.
Yeah, I want to maybe mention one thing that I found very useful in academic research, which is automatic machine learning. There are now packages that basically do the whole pipeline of machine learning for you. These packages will often outperform PhD students who have spent much of their life working on better classification techniques. Why and how does that work? Like AutoML, for one package is, for example, AutoSKLearn. I like it very much. What it does is you can say, well, if you're a really well-trained data scientist, you know which of the 10 techniques, like support vector machines or k-nearest neighbors, or like maybe some simple neural network, which method is good for which problem. That's at least what people believe that they learn. Now, that is totally useless information, because we live in the time where compute is pretty cheap. So AutoML, basically, how does it work? It just implements all 10 popular techniques. And on that data set where you predict Y from X, it basically tries all 10 of them. And then it tries all kinds of hyperparameters. And then it basically glues all of them together into really good estimates. Mm-hmm. For us users, it takes all this complexity of machine learning out of it. I basically say, hey, AutoML, here's my feature matrix and here's my label vector. And you have 1 hour. I'll come back once I am finished with my coffee. You come back and it will often do better than what people do. In fact, what we find in meta-analysis is that on average, it does better than scientists, at least in some dimensions. So this means that we go into that domain where a lot of the tools we need as data scientists, they are starting to be very simple on the machine learning side. They're not simple on the domain expert side, which is, okay, hold on. What do we predict? What do we all want to optimize? What does it mean to be successful at that? And so I think this thinking is underappreciated these days.
Yeah, exactly. The success of data science solutions is not just the accuracy metrics. There can be the cost related, the time spent, or like you mentioned, you have to understand this domain to define a suitable business metric to measure your success. So another question I have is, it sounds like you have a very interesting career path. So what type of advice would you give to your younger self, if you could?
On the grand scale, I have few things that I tell my past self, because I just consider myself extremely blessed and lucky, and I'm very happy with life, and I have like a wonderful family, and I just feel really good in this world. So in that sense, it's a little dangerous to give my past self advice. But of course, I mean, like, look, I made like strategic mistakes at times. And I mean, maybe that's interesting for people to hear. So it must have been like 2000, when was that? Like 2007, maybe 2008 or something. And I was postdoc at MIT. And I remember how I explained there were some people there who worked on neural networks. And back at the time, it felt that modern machine learning, which was support vector machines at that point of time, was really logical, and neural networks were not. So I basically told them, look, like, this is like, neural networks are really the wrong path, because you can't like explain to them your proper beliefs about the world. And let's just say I had to eat those words, because like neural networks, deep learning is everywhere now and is like driving all the things. But it seemed, based on what we knew at that point of time, very logical. And I did neural networks in 2000, 1999 or earlier. And I was fitting neural data with it. And I kind of abandoned that idea because I too was dazzled by the bubble back then. The bubble back then wasn't deep learning. The bubble back then was like statistical learning theory in a way, like not like we were talking about VC dimensions and all things like that. And so of course I could like give my past self kind of like tools to bootstrap those things and kind of get out of bubbles and like not make scientific mistakes. But again, it would be very dangerous. Not like I might end up being very sad by having presaged certain things.
Yeah.
So, but I think in a way, like not following the bubbles would probably be my advice. So when neural networks were dying in the early 2000s, I shouldn't have followed the end of the bubble. And when and similarly, like Bayesian techniques were like all the rage back then. Everyone was like, the future of machine learning is Bayes, and now it's just like, it was what? Why? And I think I think in that sense, I was following like the trends, maybe a little too much. But then at the same time, the field learned a lot from that. Like a lot of ideas that are in a way Bayesian, you see them in deep learning, and like a lot of ideas that were there in old neural networks went into a Bayes. And so in a way, these bubbles, like they always learn from the previous bubble. So it's not that it's lost, but I could be cited more often than I am now, and maybe I would have more grant funding, and if I would give such hints to my past self.
Yeah, that's great advice. And then to follow up in terms of bubbles, what are some bubbles right now that you think?
Oh, like deep learning is obviously the obvious one. No, and I'm saying that despite the fact that I teach it, deep learning clearly belongs into everyone's tool chest these days, or like every data scientist tool chest. At the same time, we view these systems as being like so intelligent and so forth. They are not. Like the way deep learning is very productive primarily for images and natural language processing. And they're both domains where we have very strong priors, and they're both domains where we basically have infinite amount of data. And like we are training our transformers on basically all the text, or a significant proportion of all the text that has ever been typed by human beings. So it's we're in these super data rich domains there, and it looks wonderful there. But in reality, or similarly with like playing games like Go, sure, they have millions of games and they get really good at that. But but arguably, like the question is, are we more or less doing like regression? Like basically we just, like the most malicious view of machine learning is it's just this really simple thing where I say, well, if you have two data points that are similar, and similarity is kind of something we can debate about, but you have two data points that are similar, then like the labels associated with them, or the things that I predict with them, will kind of be similar. And in a way, much of machine learning boils down to like this very, very simple idea. The question is like, how much extra do we have? And now you can say, well, convnets add an extra to it if we have two things that are like very similar and they're both moved. Then the output should be very similar. And that's great. And by all means, and it scales wonderfully and so forth, but we assign it with this level of intelligence, and I'm not sure if it has that. So GPT-3 writes like wonderful sentences, not like, but it doesn't understand anything. Like if I prompt it with like, there's this group of unicorns, it sort of says, this group of unicorns all have two horns on its head. It's like, hold on, I just told you it's unicorns. You even just repeated that it's unicorns. You don't understand the concept of unicorn. And so in that sense, there is a history of the field of machine learning, and you can maybe ascribe it to people like Ben Recht there, where you can say, machine learning every 20 years or so discovers that there's a whole bunch of problems you can solve with like this local regression thing.
Yeah.
And then they discover that it's like, in the end, it can't solve all the problems in the world. And then everyone forgets about it. And some later point of time, someone's like, hey, we can build it bigger with more data or something. But the problems remain. Like what we call AI can't causally think. It has great trouble with the fact that the world consists of things. It's very bad at generalization relative to humans. And it has great trouble kind of seeing the world we do in terms of like meaning and causal relationships and all that. And little in the developments of those fields have happened to convince us that these problems are going to go away. AI is not, like deep learning is not solving those. Yeah. If anything, deep learning is forgetting about them, because they're in this domain where if you have like just enough data, you can hope that you can basically look like you're intelligent just because.
Yeah.
No, basically it's like, here's a new prompt. What is the most similar prompt in the history of mankind to the prompt that you just gave me? Most of the time you will be great because well, a lot has been said, a lot of prompts have been used. And so in that sense, there's like real reasons to be doubtful about like how strong our methods really are.
Yeah, I agree with that. You know, we talk a lot about your career, your research. I'm curious, so who you are when you're not doing research? What do you like to do for fun?
I like to do a lot of things for fun. So it depends on the season. All year round, I love dancing salsa. And you said you were a director for arts at some point of time.
Yeah, I also dance salsa.
Nice. Yeah. Wow. And my wife and me, we choreographed the University of Chicago team at some point. Wow. So we are very serious about our salsaing. We are on 2 New York style dancers, if that means much to you.
On 2 is hard. I do on 1.
There's 2 tribes of 2 tribes of salsa, as some of our audience will hear now for the first time. So we love salsa. Then in summer, we love to hike all the mountains, everywhere, camping, all that. And in winter, I'm a big time skier and snowboarder.
Oh, wow.
It matters a great deal to me. And I just really love being in the outdoors.
Yeah. Oh, that's great. You have different hobbies that's suitable for different seasons.
Well, what's your choice? You can't like survive half a year without hobbies. That would be just too sad.
Yeah. Do you ever get inspired by dancing or going to the mountains that get ideas when you're doing those activities about your research?
I don't know. Like my process of ideas usually is centered on people. And that's why the pandemic was just so bad for me. Like my creative process is like, I meet people, usually they're experts on something. And then I start asking like very naive questions about what they do. And then I kind of try and like brainstorm like what data could in a way do in that domain. And so that's often like where ideas come from for me. They come from like being with people and like having coffee and like joking around and kind of thinking differently in new ways about old problems. And so in that sense, I don't think that like these other the hobbies that I have, that they really directly help with that, but they certainly help by keeping me happy and focused and centered and kind of allow me to be me when I'm with people.
And exercise different part of your brain, which is important.
That's right. And oh yeah, hold on. And one more hobby, I like to do CrossFit. I've recently, during the pandemic, I've really gotten into going to the gym and lifting weights and all that, and it's great fun.
Yeah, that's awesome. CrossFit is hard. I tried it once. So before we wrap up, what is something in your life or in your research that you're very excited about?
Something in the life I'm excited about COVID coming towards an end. So excited. I mean, like, okay. Yeah. And I should say, I'm one of these overly optimistic people. I was hoping that COVID was about to end for like a year and a half. I was always, in a few months, it's going to be over, and it never was over. But like, that's definitely in my private life what I'm most excited about. When it comes to my scientific life, right now, I'm actually quite excited about evolution. So I thought a lot about two ways of thinking about brains in my past. You can say one way of thinking about brains is that I say, well, they're made out of neurons. How can neurons do things? And that's the bottom-up way of understanding brains, where I can say, I want to understand how we think in a way by looking at like how cells put things together. But in a way, this is very difficult. And we recently wrote with Tim Lillicrap, we wrote a preprint where we argue that it might even be fundamentally impossible. But that's one strand of neuroscience. Another strand is what we call normative, where I'm like, okay, what would it mean for a brain to work optimally? Now, what does that mean for behaviors? Can I predict your behaviors or your neural data based on that way of thinking? And then there's a third way of thinking, which comes from evolution, where I can say, okay, what can I say about like the history? And I think there's interesting things about evolution that we can have there. For example, and I read a wonderful book about that. It's called The Plausibility of Life, if I remember that right. And it asks what is generic that we should expect. And there's one phenomenon that often happens that you could say I could specify how a brain is set up, basically how every nerve cell interacts with every other nerve cell. But then evolution would grind to a halt, because what if I want to add like a new brain area? I would need to, like, every single cell I'd need to first pre-specify. So it would be very hard. So there is this trend that people speculate in evolution, where things move from being pre-specified, from the genetics, if you want. They move into the developmental process, where you could say, instead of saying how everything is connected, I in fact set up like a set of learning rules and objective functions and all that. Yeah, it will ultimately give rise to a system that works. So and that allows evolution to be much faster. Now you can say, maybe the brain does something like gradient descent, I add a new brain area, no problem. No, like I can always take a deep learning system, I add like one layer of neurons, no problem. The gradient descent will fix all of that. And I think that therefore this evolution-like thinking can be very rich for thinking about brains. And so recently I spent a lot of time just thinking that, and in large parts this because it's a set of ideas that the field isn't currently thinking about, right? It's an opportunity to be curious about something new, and go away from that area where lots of people are doing similar things that I do now.
Yeah, that's very exciting. Do you plan to write a book once you have figured out those ideas?
Yes. So I'm thinking about writing a book that leads to that thinks really deeply about gradient descent. And you can say gradient descent is kind of an organizer of a lot of things in our lives and in the world that is around us, and in the domain of evolution, as we discussed earlier, and arguably in a lot of other domains as well. So I started talking with a colleague about like how we could write a book around that.
Yeah, that's a great idea. I also thought about it. I sometimes think about what are some life lessons we can learn from the algorithms, from especially deep learning algorithms.
Certainly. Now you can say, what does it mean to do Adam in real life? Like when it comes to optimization algorithms, there's this idea that we want methods with momentum. Arguably, we want to build that into human decision-making. You did more of X, it was good. Yeah. Now keep going, do even more of X now in the future, because like you just figured out that X was the right direction. So there's probably a lot of ideas like that, where we can take insights from insights from algorithms broadly construed and apply them to our everyday life.
Yeah, and also in some use cases, we don't always have to find a global maximum. Sometimes locally optimized, sometimes it's good enough to solve the problem in time. In terms of decision making, we don't always have to look at a manual and study the best solution to find a best course. Always advocate. Sometimes you need to have a deadline for yourself to make the decision that's fast enough.
Yeah. You can say doing 1,000 things a little bit better might be much more important than doing one thing perfectly.
Yeah. So Konrad, this is a great conversation. It's a pleasure. And I learned so much from you. For people who want to reach out to you or find you on the internet, where can they find you?
The easiest is probably Twitter, where I'm at Kording Lab. And then otherwise I'm on LinkedIn, but I only check that every couple of days.
Great. Is there something else you'd like to share with the audience, with the listeners?
Well, let me come back to my recommendation from earlier. If you want to understand why I'm so excited about causality, read the book of Why. If you're interested in why I'm so excited about evolution, read the book of Is Life Plausible? Or The Plausibility of Life.
That's great. Thank you so much, Konrad.
Oh, wonderful. Great to see you, Daliana.